our galaxy. By measuring the star's distances, they found a galaxy in its own right, far outside the Milky Way. The Andromeda Galaxy is more than 2 million light years from us. So we see it as it looked more than 2 million years ago, long before humans first walked the Earth. As they probed deeper and located many more galaxies, the astronomers were startled to see that the light from distant galaxies was always stretched out to longer, redder wavelengths, signifying that they were all moving away from us. They found that the more distant a galaxy, the faster it's moving. Cosmic space is constantly stretching, carrying the galaxies with it. But there's no center to the universe. An observer in this galaxy would see the same evidence of cosmic expansion as we do. So would observers in that one there. Wherever you are, it looks as if you're at the center and everyone else is speeding away. As the universe expands, it cools, its energy thinning out across a growing volume of space. The overall temperature of the cosmos today is only 3 degrees above the coldest possible temperature, absolute zero. But if we ran time backward, all that energy would be compressed into a shrinking volume of space, and the universe would get hotter. Realizing this, a few scientists calculated that the entire universe must have once been hotter than the sun. Skeptics ridiculed the idea, naming it the Big Bang Theory. But then, in 1964, 2 astronomers at Bell Labs in New Jersey started testing a horn-shaped radio antenna. They wanted to detect the natural radio waves produced by gas clouds in space. Instead, they encountered something they couldn't explain. Low-level energy coming evenly from all directions in the sky. Without realizing it, they had made one of the most profound discoveries in human history. Light from the Big Bang itself, released when the universe was only 380,000 years old, less than 1/100th of 1% of its current age. Evidence of the Big Bang was written all across the sky, in the glow of what is now called the cosmic background radiation. Satellites have since mapped the cosmic background radiation in detail, revealing how matter and energy were distributed in the infant universe. In this map, created by the Planck satellite in 2013, the slightly more massive regions are colored blue. Over billions of years, they went on to form clusters of galaxies. The less massive regions, colored red, became cosmic voids. Because it takes time for the light from distant objects to reach Earth, everything we see in the sky belongs to the past. These spheres mark distances from Earth in light years. When we observe galaxies billions of light years from Earth, we see them as they looked billions of years ago. We're flying through a three-dimensional atlas of millions of galaxies. The gaps are regions we have yet to map. Beyond every galaxy we could ever observe, farthest away in space and furthest back in time, the cosmic background radiation marks the visible edge of our observable universe. Yet, evidence of what happened even earlier in cosmic history can be found, right in our own neighborhood. In 1995, NASA's Galileo spacecraft released a probe to study the upper atmosphere of Jupiter. Scientists had calculated that the simplest atoms were forged during the first minutes of the Big Bang. One of them, heavy hydrogen, is destroyed inside stars, so it should have become ever rarer as the universe evolved. Unlike Earth, Jupiter acts as a cold storage locker, preserving samples of the materials from which the solar system formed more than 4 billion years ago. By analyzing the giant planet's atmosphere, scientists could check how much heavy hydrogen existed back then. Observations of the cosmic background radiation had established that the universe was once hotter than the surface of the sun. Galileo's audacious exploration of Jupiter found enough heavy hydrogen to confirm that during the first minutes of the Big Bang, the entire universe was hotter than the center of the sun. Hot enough to forge simple atoms. But while scientists were piecing together the history of atoms, evidence emerged that most of the matter in the universe isn't made of atoms at all. The universe contains clusters of galaxies, like this one. Each cluster, home to trillions of stars, generates enough gravity to warp the space around it into a giant lens that distorts our view of the galaxies beyond. But when we calculate the strength of these gravitational lenses, we find that each cluster must contain 6 times more matter than we can see there. So now it seems that all the glowing stars are just the glittering froth on a dark cosmic ocean of invisible stuff called dark matter. The motions of galaxies within each cluster confirm the presence of dark matter. The galaxies orbit too fast to be held together by the gravity of normal matter alone. Remove the dark matter, its lensing stops, and the cluster flies apart. Scientists find that dark matter, shown here in black, was essential to forming the large-scale structure of today's universe. This computer simulation traces how cosmic structure evolved over time. The bright knots contain thousands of galaxies drawn together by the vast sheets and tendrils of dark matter. These knots grew from the densest regions seen in the cosmic background radiation. The less dense regions of the background became cosmic voids, big, empty bubbles, hundreds of millions of light years wide. The gravity generated by normal matter is much too weak to create this cosmic web. Dark matter must be doing the job. What is dark matter? Scientists are conducting experiments to find out. Some of their detectors are buried deep beneath Earth's surface to minimize interference. One detector, mounted on the International Space Station, looks for signs of dark matter particles interacting far across the galaxy. While scientists expect that dark matter particles may soon be found, another mystery has emerged that's changing how we think about the future of our universe. Astronomers had thought that the gravity exerted by all the matter in the universe would slow down the rate of cosmic expansion. To check this prediction, teams of observers charted the distances and speeds of extremely remote galaxies by studying exploding stars called supernovas. As this time-lapse view of the Milky Way shows, stars explode fairly often, at a rate of about 2 per century in a galaxy like ours. So, if you observe enough galaxies, you can spot a new supernova every few nights. The observers were especially interested in a particular type of supernova, like this one, where the corpses of 2 dead stars orbit each other so closely that they eventually collide and detonate. Such supernovas are very bright and consistent in brightness, providing scientists with an extraordinary tool for measuring cosmic distances across the universe and back through time. By measuring the distances and speeds of hundreds of supernovas, the astronomers learned how fast the universe was expanding billions of years ago. By 1998, to their astonishment, they found that the universe hadn't expanded faster in the past as expected. Just the opposite. It used to expand more slowly than it does today. The expansion rate isn't slowing down, it's speeding up, accelerating. It has been accelerating for the past 5 billion years. The pressure causing the acceleration is called dark energy. But that's just a label. Nobody yet understands dark energy, though it appears to be powerful enough to shape the course of cosmic destiny. Matter and energy are two sides of the same coin, as Einstein revealed in his famous equation, E equals mc squared. In those terms, dark energy weighs in at nearly 70% of the total stuff of the universe. Dark matter accounts for almost all the rest. Normal matter, all that we are, or all that we've ever seen or touched, amounts to less than 5% of the known universe. So we know precisely when the universe began, and we're beginning to understand what it's made of. But how big is it? Our observable universe is limited to the part of the cosmos from which light has reached us here on Earth. But every galaxy occupies the center of its own observable universe. Observers in this distant galaxy can see light from regions we cannot yet see. And we can see regions they cannot see. So no matter who or where you are, you'll reach the same conclusion: that the universe as a whole must be bigger than the part of it you can perceive. How much bigger? Some scientists speculate that if the observable universe were the size of a planetarium dome, the entire universe would be larger than planet Earth. Others suggest it may be infinitely large. Clearly, there's more to the universe than meets the eye. The Big Bang happened long ago, but not far away. It happened here, there, and everywhere. Peering into the dark, we stand on the threshold of great discoveries. And we always will, as long as we keep exploring.